there are two different types, Fischer and Sharp. Here are the types. Gross catalyst is a Fischer carbene. It is an NHC catalyst, which is the type of catalyst that we work with, and it is used in olefin metathesis, which is used in the production of pharmaceuticals. The other type, Schwab carbene, is also used in olefin metathesis. And these are the N-heterocyclic carbenes, or NHCs, that we work with. They're generated from the corresponding azolium salts, and they are efficient spectator ligands in catalysis, specifically hydrogenation, cyclization, alkene metathesis, and organic synthesis. And they can be tuned electronically and sterically by changing the wingtip. As you can see in the figure that I have, the R groups on either side bonded to nitrogen are the wingtips that we were able to change to tune the effects of our catalyst. Next are catalytic reactions. What is a catalyst? A catalyst speeds up the rate of reaction. It allows for a lower energy of activation. It has alternative mechanisms, and they can participate 10 to 10,000 times in the catalytic cycle. This means that you can have a very small amount of catalyst and get a very large yield in your product. The importance is it allows high energy reactions that happen at much lower temperatures, and 80% of industrial reactions use a catalyst. Here is a graph showing what happens without a catalyst, and then with the catalyst, as you can see, the energy of activation is much lower, and this shows a two-step mechanism, but you can have even more mechanisms or steps within your reaction. Next is heterogeneous hydrogenation reactions. This is the precursor of the transfer hydrogenation reactions that we use. This was the original way of reducing double bonds with hydrogen. However, hydrogen gas is very flammable, which made it dangerous for the people working with it, and the catalyst stays solid throughout the reaction, therefore it is called heterogeneous. This reaction shows platinum being used as our catalyst. Next is homogeneous catalysis. This used catalysts such as Wilkinson's and Crabtree's. This still used hydrogen gas. However, the catalysts were homogeneous. This means that they were dissolved within our solution. Next is transfer hydrogenation. This is the type of hydrogenation that we use. It is the safest type because the source of hydrogen is isopropanol, which is a solvent as opposed to hydrogen gas. The isopropanol is oxidized and our substrate is reduced with very high yields. And it reduces ketones and amines well, which is hard to do heterogeneously. Here is a general reaction scheme for transfer hydrogenation. As you can see, the hydrogens at the top that I circled are on the solvent, and then after the reaction happens, they have been transferred over to our substrate. This reduces the double bond that we have in our substrate. The other type of reaction that we tested is the cyclization reaction. The reaction scheme is in the top right. It allows for the formation of cyclic compounds. Reaction tested creates a carbon-nitrogen bond, and it is a very important reaction. It is used in the synthesis of anti-cancerous, anti-HIV, anti-inflammatory, and other types of medicines, as well as other useful compounds. This reaction might be the most important one that we have tested to date, and has a lot of real-world applications. This is our project. We're working on the synthesis, characterization, and catalytic efficiency of new green chemistry iridium and rhodium NHC complexes for both transfer hydrogenation and cyclization reactions. This is the general figure for our complexes. As you can see, there is a metal center, either iridium or rhodium. There is a wingtip that we changed. It was either a methyl or neopentyl group. This mostly changed the steric effects of our NHC. And then we also had an L group. Once the L group was added, we had an ionic complex, and we used 4 different L groups, either triphenylphosphine, tricyclohexylphosphine, pyridine, and a second NHC. So first, the synthesis and characterization of our complexes. The first step in this process made a triazolium salt. We started with a triazole that had our wingtip attached, either our methyl or neopentyl group, and through a reaction with isopropyl bromide, we made our triazolium salt. This step in the reaction was extremely difficult. You cannot buy these products on the market because of how challenging the synthesis is. We got yields of 5 to 10% even after 3 days phase of reaction. This means that we had very little to work with, and the rest of the steps in our synthesis had to work very well. The next step was our synthesis of metal complexes. We took our trisolium salt, we reacted it first with silver oxide, and then with our metal cod group. This created the neutral complex 3 that you can see. Once we had our neutral complex and confirmed it with nucleomagnetic resonance spectroscopy, we then reacted it with silver tetraborofluorate and our L group, which made our cationic complex 4. As you can see, a group of our BF4 is bonded to our cationic complex. This table shows all of our catalysts synthesized. We synthesized 9 complexes and tested 7 out of the 9. Ones that I would like you to focus on are 4B as well as 4F. They both have a rhodium metal center as well as a tricyclohexylphosphine L group. The only difference between the two is the R group, either methyl or neopentyl. This will come up later when we talk about our catalytic testing. Next is our NMR spectroscopy data. This shows our reactions as we go down from our isopropyl bromide all the way to our neutral complex. As you can see, the peaks get carried on through the reactions. Something I would like to note is in the bottom right, there is a peak around 140. Once this NHC group gets attached to our rhodium center, the peak gets shifted all the way down to 180 as we see here. This shows a closer look. As you can see, the doublet that I showed at 180 is our rhodium attached to a carbon. We know that we got a rhodium-carbon complex because we have a doublet. Rhodium-103 has an atomic spin of 1/2, which means that when it is attached to a carbon, it splits the peak of the carbon, and also rhodium comes in an abundance of 100%. This means that we got a clean doublet as opposed to a painted one where you would have a doublet, but then there would be another peak in the center of it. Next is our X-ray diffraction data. This is the data that we ended up publishing. This data was very important. It gave us a 100% clear picture of what we got. This is not a model. This is the actual representation of our crystal structures. This is our first neutral complex that we synthesized. As you can see, there is a rhodium center with our NHC with each of our wingtips, as well as a cyclooctadiene group. This is a cationic complex. This one has an iridium center, as well as a tricyclohexylphosphine group, which you can see is over on this left side. As you can see, it is a very bulky group, which we think help in its catalytic effect, as well as our NHC and our cyclooctadiene. I labeled the 3 parts of this complex. There is our cation, as well as an anion of BF4, which you can see here. And then we also had some solvent of CH2CO2, which crystallized with our structure. In the bottom left, here is the figure for the X-ray structure that we got. Next is the unit cell structure of the complex on the previous page. This was an extremely unusual unit cell. We were very surprised when we got it because it has a Z value of 8. This means that 8 molecules crystal per unit cell. This is something that is unprecedented, as you never see a very large group have such a large Z value. We're not completely sure why this happened, and part of our further research will be understanding why we have such a large unit cell. Next is our catalytic testing. This is the result of our synthesis process. This will show us which of the catalysts we made was the best in our different types of reactions. We started with a ketone hydrogenation reaction. This was just to clear that if we changed the ketone, there wasn't a vast difference in our percent yield. As you can see in the table, there was some slight variation, but this could be due to human error. Once we have the confirmation that our ketone doesn't matter too much, we're able to move into the testing of all of our catalysts. We tested them on two different complexes. One had a carbon-oxygen double bond and one had a carbon-nitrogen double bond. As you can see, the reaction schemes are here. We tested 7 catalysts, and we found that 4F was the best in this type, having a 100% yield of N-benzoyl and a 98% yield of acetophenol. 4B also tested very well. These are the two catalysts that I told you to note earlier, and in the top right is catalyst 4F. Next, we tested the reduction of carbon-carbon bonds. Carbon-carbon bonds are much more difficult to reduce than carbon-oxygen or carbon-nitrogen. We tested both non-polar and polar double bonds. As you can see, catalyst 4B tested very well, higher than we had expected, and catalyst 4F had 100% yield even with a non-polar carbon-carbon double bond. This is something that we were not expecting, and we are very excited to see the efficiency of catalyst 4F. Next is selective hydrogenation. We did this catalytic test to see if each of our catalysts would reduce a ketone over an aldehyde or an aldehyde over a ketone. As you can see, our aldehyde percent yield was 100% reduced, and the ketone percent yield was very low, 16 for 4B and 13 for 4F. This means that our catalysts were able to selectively reduce the aldehyde as we had. Next is one-pot synthesis. This is very similar to the carbon-nitrogen reduction that we tested earlier on all of our catalysts. However, we took it a step further and started with our basic reactants, and then we made our carbon-nitrogen double bond, and then added our catalyst to test. This muddied the waters, so to say, and even with that, we still had a very high percent yield for 4F and a very high percent yield for 4B as well. Our last type of catalytic test was the cyclization reaction. As I noted earlier, this is a very important reaction used due to its synthesis of many medicines. We were able to find a literature value in the NMR that we got after our reaction matched it. There are two possible products, either an indole or an oxyindole. We had a carbonyl if we had our oxyindole product, and this was confirmed using IR spectroscopy. We were only able to test this on catalyst 4F so far, and it had a very high yield. It went remarkably well, and it's something that we wish to further test in the future. In conclusion, we synthesized 9 new complexes. Our rhodium and iridium tricyclohexylphosphine complexes showed excellent catalytic activity and transfer hydrogenation reactions. Our neophentyl wingtip showed promising catalytic activity over our methyl wingtip, and catalyst 4F was the best overall. This shows a table of all of the percent yields for catalyst 4F. As you can see, in every single benchmark reaction, it tested over a 90% yield. And this is a figure of catalyst 4F in the top right. For our future plans, we wish to study the electronic effects of the different wingtips by making the carbonyl complexes of each neutral complex. And we already studied the IR spectroscopy for our carbonyl complexes. This is the reaction that we use to make said carbonyl complexes, and this is a reaction that will continue in the future as we continue to test. I'd like to make some acknowledgments as well. Ms. Karen Murley for her part in our summer research, very generous funds for that, as well as Dr. Roger Seelan. Dr. Albert for his part in our crystallography analysis. This was key in us being able to publish our data. As well as Mr. Steve Purifoy, he helped with our instrument use, as well as the Department of Chemistry at Millersville. These are the references used in this presentation. Thank you, and do you have any questions? this is something that we are going to study further. We started with our steric effects. It had two larger wingtips on our NHC, which we believe could have affected it. This is because when we tested our methyl and our neopentyl with everything else being the same, it reacted better. We also tested it with our IR. This was something that we're going to have to study.
You think bigger will continue to be better, or is it?
To an extent, we are not sure exactly how much it will be better, but this is something we can continue to study.
Can you go back to slide 36? Yeah, are you making an imine in base? Does that work well? I thought the pH has to be below 7 to make an imine.
So yes, it did actually work well. After the first step, we tested it with NMR to confirm that we got what we.
That's awesome. I thought pH had to be. Does this work in acidic media then too, or for other amines? Because amines are usually formed in acid. Can you do this in acid, or will the complex fall apart?
That's not something that we have personally tested.
I was just curious, like, because imine, if you can reduce an imine with this, and amines are usually made in acid, like that'd be awesome. Like your stuff's not acid sensitive.
Yeah, all the amine reductions were in the base medium.
Okay. We usually do our amines in acid. Well, you know, we do all of our amines. We do our amines in acid, so that's really cool.
This was a weak base,
Right.
potassium carbonate.
Right.
I'm sure he will tell you as well, when we had the aldehyde as the ketone,
Yeah.
when you try to reduce it with potassium hydroxide, the Cannizzaro reaction.
Right.
So we had to use a milder base.
But you can't do this in acidic conditions, like.
No, it formed pretty easy straight away. Because even if you, without the one-pot synthesis, if you take the imine with the catalyst, even those reactions were in basic medium, the reductions. Any other questions for Josh? Let's thank him again.